This meeting is being recorded.
We have seen in the past that ethers are generally unreactive under basic or mildly acidic conditions. So therefore, we use them for a variety of reactions as solvents. But there are some reactions that ethers can undergo. So we're going to explore those in this section, section 13.6. The first of which is something called acid cleavage. So what we'll see is that when an ether is heated with a concentrated strong acid, such as HBr or HI, it can undergo this acid cleavage, and the product would be two alkyl halides. So that's what we see here. We see in this first alkyl halide formation, we have a proton transfer, which adds a proton here, generating this oxonium ion in this first step. What then happens is the halide ion that is released in that first proton transfer acts as a nucleophile and then attacks this oxonium ion and ejects an alcohol as a leaving group. So this is our leaving group here, and this is our first alkyl halide that has formed. When we form our second alkyl halide, now that alcohol that was formed is now protonated, generating our intermediate here, that oxonium ion. Again, we see that SN2 reaction, that nucleophilic attack, and now water is our leaving group, so that's our Lg, and this is our second alkyl halide that has been formed. So we can see that ethers do react and undergo this acid cleavage to produce alkyl halides. And as mentioned, this can work with both HBr and HI, but commonly we do not see this happen with HCl, which is much less efficient, and HF does not cause acidic cleavage. So these are the two reagents that you would see. If we have an ether reacting with either, we'll produce those two alkyl halides. If we have an R group that is tertiary, then this cleavage would occur instead of SN2 under an SN1 mechanism. And we should also know that if our R group is aryl or vinyl, we don't see a substitution occur. And we actually would see, so say we have this R group here, and if we heated it with excess of that strong acid, this would remain a phenol, and the other side does not have that substitution occur. So this R group can be substituted, and we can form one alkyl halide with this phenyl ether. But on the other side, the benzene ring does not have that substitution process occur because it is an sp2 hybridized carbon in that ring. So those are some specifics of this acid cleavage that we should look out for. Another reaction type that ethers undergo is auto-oxidation, just from being exposed to atmospheric oxygen. So that's what we see here. We see O2, and this is generally a slow process to form these hydroperoxides. So this is actually occurring through a free radical mechanism, which O2 exists as a free radical, but we would have an initiator of some source here that would perform this hydrogen abstraction and produce this carbon radical here that we see. And then that would react during the propagation step with the atmospheric oxygen here. So molecular oxygen, we're told, would couple in this step, this propagation step, with our carbon radical that was formed in our initiation step. And this progresses through a second step in propagation here during this hydrogen abstraction, and this would produce a new carbon radical, our ether, that would continue this propagation, and until we reach a termination step, which we'll see is also a coupling reaction. This would destroy the two carbon radicals, and we would have this other side product created. And if you recall from our chapter on radical reactions, chapter 10, we saw that the net reaction would be the sum of the propagation steps. And this here, after canceling out some intermediates and some other products that are seen as both products and reactants, this is our net reaction down here. We already have our RH, our alkyl halide, or I'm sorry, our RH, our being auto-oxidized, so this could be our ether, and then we form this hydroperoxide here. So we will cover the next section, section 13.7, in our next video.